My name is Emmanuel, and with me today is Rohit. Over the past decade, we have been in different roles, from security research to pen testing to red teaming, and recently security engineering. So the stuff that we'll be talking today is based on our experience and perspective from these different roles. Now, container is a very broad topic. There's so much to talk about, and we can't possibly cover everything today. Instead, what we are going to do is to focus on just the Docker and the Kubernetes environment. We'll go through some common examples of vulnerabilities that we see, from breaking out of these containers to lateral movement. And today, we will also be releasing a tool called the Docker Exploitation Toolkit. This is basically a collection of mini tools that we have created. It follows the Unix philosophy whereby each tool does just one thing, but does it well. Now, as a pen tester, as a red teamer, very often the first instance that you realize you are in a Dockerized environment is when you actually gain remote code execution. You compromise an application and you realize that, hey, you are in a restricted environment. And the goal now is to actually break out and escape out of this restricted environment. And as a pen tester, as a red teamer, it really makes our life easier when we realize that a container is running in privilege mode. For those of you guys who have been dealing with Docker for a while, I'm sure you have seen people running Docker containers with -- privilege. Or maybe like even you are guilty of this yourself. But what is this? What is this -- privilege? Why is it bad? To understand that, you got to realize that when you run Docker, by default, it comes with a whole bunch of restriction. There's restricted Linux capabilities. There's seccomp to filter and restrict syscall. There's AppArmor to restrict mount operations and preventing write access to sensitive locations. Now, all of this goes away when you run a container in privilege mode. But as a developer, what does it really mean, right? I mean, we know that it's not too good from a security perspective, but from a pragmatic perspective, what does it really mean for me? What this means is that the exploit to break out of a privileged container can fit in a single tweet. I'll let that sink in for a moment. That's 140 characters to break out of a privileged container. Now, this was initially disclosed by Felix Wilhelm, really smart guy. And even though it's only 140 characters, there's actually a lot of things that's happening behind the scene. And I'm going to break it down for you. The first step is to try and figure out a mapping between the file system in the container and the file system in the host. Say, for example, if within a container, you create a file called exploit.sh, it is possible to reference this exact same file from the host itself. But obviously, the path from the host is going to be different because they're mounted differently. So the first step is to actually try and figure out the mapping of the file system between the container and the host. Now, the second step is to find C group with release agent. C group or control groups are basically kernel features that enforces limits and constraints. For example, you can limit the memory using C group for a specific container, right? And the way to interact with this C group is through like a pseudo file system. And within C group, there's a special configuration called release agent. This is basically a mechanism whereby it gets triggered when there's no more processes running in the C group. This is a feature that people use for cleanup or for monitoring or for alert. So this second step is to figure out which are the C groups with a release agent available. And now the third step is to actually configure the release agent to run the exploit.sh we created in step 1. The path for this file needs to be from the host point of view, which is why we need to figure out the path mapping in step 1. Now, typically, writing and configuring the release agent is not possible in a Docker container because it is read-only. But in privilege mode, this becomes read-write. So you can use that to configure the release agent. Next, the next step is to actually enable that release agent via notify on release. Basically, once you enable this, it says that, hey, when there's no more processes running in that C group, notify the release agent. Again, typically you can't write to this, but in a privileged container, you get read-write capability for this. And the final step is to actually tie all of this together. First, you start the process, you add it to a child C group, and immediately exits. So now there's no process tied to that C group. This triggers the release agent because notify on release is set to enable. And once that release agent is triggered, it runs your export.sh. And ladies and gentlemen, this is how you break out of a privileged container in 140 characters. So now you know that, hey, it's really easy and trivial to break out of a privileged container. You got to be wondering, like, who runs container in privileged mode, right? I mean, this is actually more common than you think. When you run a tool in containers, say for example, TCP dump, and you want to use certain configuration, some of these Docker default restrictions actually stops you from doing that. So the proper way of doing this is to figure out what are the Linux capabilities that you need. There's probably a little bit of trial and error here. Or you can just run your container in privileged mode and everything just works. And humans tend to choose the path of least resistance, right? If you do a quick search on GitHub, you'll notice that there's about 140,000 of containers running in privileged mode. So that gives you a sense that, hey, this is not as uncommon as you think it is. Now, the next misconfiguration or vulnerability that I want to talk about is regarding Docker socket. Docker socket, when you install Docker, by default, it creates this Unix socket. And this is the interface through which you talk and interact with the Docker daemon. Say on the CLI, you do a Docker pull or Docker run or Docker start. It talks to this Unix socket and tell the Docker daemon what to do. And the thing is that this Docker daemon runs as root, so it is highly privileged, which means that access to this Docker socket needs to be restricted. Sometimes we see that people actually mount this Docker socket within containers itself. And this is bad because this means that within the container, you can now talk to the Docker daemon and ask it to do stuff, right? Using this, you can actually break out of the container or even like escalate your privileges within the host itself. And I'm just going to give a quick demo of a tool that we created to help to do this exploit easily. And this tool is called Houdini.
Okay, in this terminal, we are inside a container. And what we are doing now is that we are running the Houdini tool. And this tool, it checks for a couple of different vulnerabilities or misconfiguration within the container itself. And Houdini doesn't try to assume that it has tools like curl and stuff like that, because within the container, very often you don't have access to tools that we take for granted. And so what we do is that we bring in our own tools that is needed for the exploit, whether is it BusyBox or is it like a Drop Bear, So we don't make any assumption on the tools required or the tools that are actually contained within the container. And in this case, what we are doing is that we are going to exploit it by attacking the Docker socket. Um, we use it to start a container, mount the host file system, copy a SSH key into the host file system, and then we should be able to SSH from the container into the host system. There we go.
Okay. And again, if you do a quick search on GitHub, you will see that there's a whole bunch of, there's like 30,000 instances whereby people are actually mounting Docker socket. So again, this is not that uncommon. Now, sometimes when you're on a security assessment and you find that, hey, you can't actually break out of a container, and that's where lateral movement comes in really useful. The next area I want to talk about is around Docker registry. In particular, images within the Docker registry. Or to be even more precise, the file system layers in image itself. When you run Docker on the CLI, you do like a Docker pull, you'll notice like a whole bunch of hashes flying past the screen. This is just the Docker pulling all the file system layers to run the container. Now, something to note is that Docker uses a union-based file system. If you're running an older version of Docker, you're probably running AUFS. If you're running a newer version, probably you're running overlay FS. But the underlying concept is the same. The file system is based on layers. You start with a base layer. Say you install a software, it creates a new layer on top of it. And then you might configure, set certain configurations, set certain secrets, it creates another layer. Have you guys wondered like what happens when you try to delete a file? So in a union file system, when you try to delete a file, it doesn't actually delete the file itself. Instead, what happens is that it creates a whiteout layer that basically hides the file. And you start building your layers upon layers based on that. So the file itself is actually never ever deleted. And as part of our research, we created a tool called Scavenger. What it does is that it analyzes all the file system layers in an image, and it looks for whiteout layers. And the premise is that, hey, if you are deleting something, maybe you are hiding something as well. So it goes through all these file system layers, identify the whiteout, and then extract the deleted file from one of the underlying layers. So this particular attack surface area, I think a lot of security professionals probably know about this at the back of their mind. But as far as I know, we don't think a lot of people are actually talking about this or even actively searching for these whiteouts. So this is a tool that I think will be helpful on your assessment. So let me give a quick demo of this tool.
What you are seeing here is Scavenger, which is part of the Docker exploitation toolkit. And the way it works is that you point it at the registry, tell it to pull an image, let's say Ubuntu, right? And by default, it will pull the latest image from the repo. In this case, let's give it an older version of Ubuntu. And basically what it's trying to do is that it would get the image for this version, analyze the file system layers, and point out if there's any deleted files. Okay, so you can see here, each of these SHA-256 hash represents one layer in the file system. So there's a total of 5 layers it has analyzed. And you will see that for this particular layer, there's a whole bunch of files that were deleted or wiped out. And there's some smart to this tool whereby it tries to give you some indication on potentially sensitive files. So in this case, there's a warning sign that say, hey, take a look at this GPG file. Perhaps there's something sensitive on this. And by clicking on the link, what it does is that it tries to extract the file from one of the layers underneath the whiteout. And you can see that in this case, it extracted the PGP signature file. For this particular instance, it's not sensitive, but it does give you an indication as to what the tool does, how it actually analyzes the different file system layers and extract those files.
Now, let me show you some actual files we have grabbed from images, public images on Docker Hub. They range from the more mundane license keys to private SSH keys. So these are actual files we grabbed from images on Docker Hub. This has been deleted, but using scavenger, we could extract them out. And now I'm going to hand over to Rohit, and he's going to cover more about lateral movement from the Kubernetes perspective. Over to you, Rohit.
All right, thanks, Emmanuel. So after peeking into the container breakouts, let's walk through a strategy by which a red teamer or pen testers can actually perform lateral movements and then eventually maintain persistence in a Dockerized production grade environment. Now, in case of a production grade environment, you won't see isolated Docker images, but you will always need some kind of orchestration systems for that. And that's typically needed because you have hundreds of these Docker containers to manage. Now, in all these orchestration systems, there are a bunch of them. And in this talk, we are going to focus mainly on Kubernetes-based attacks and ways to actually defend it for that. So the Kubernetes provides a way to manage the cluster of these containers. So it provides easy to use APIs where you can scale up, scale down the different parts of the containers. It also provides the self-healing capabilities. And there is a good overall community support around Kubernetes. So as a quick refreshers, because these terminologies will come time to time in our discussion, a few terminologies specific to Kubernetes. So the Kubernetes has a concept of nodes. So the nodes are nothing but hosts, could be the physical hosts or virtual machines on which your containerized environment is executing. And then it also introduces one more layer of abstraction called as pods. So the pods provide a way to run one or more containers that provide a similar kind of functionality. So these pods are then scheduled to run on nodes, that is on the host systems. Just a few minor details to remember. Now, all this overall Kubernetes-based environment is going to add a lot more burden in your already expanded threat surface. Because as you have seen in Emmanuel's talk, there are a bunch of ways in which you can break out the container. And you already have to worry about a lot more defenses in those. Things are going to get more complicated when you are in a Kubernetes production grade environment. Because there is a now authentication and authorization control that you have to manage. The way in which these pods communicate with each other, communicate with their APIs, and all of that. Kubernetes also has a control plane API server, which exposes the bunch of API. And these are powerful APIs because they provide a way to manage the entire cluster. You need to worry about the security of them. And then, as usual, like many frameworks, the defaults are often insecure in general. And then it is your responsibility as a security professional to carefully threat model it and then provide a way to actually defend against the different attacks for that. So let's walk through a technique to perform the lateral movement and then eventually maintain the persistence. Note that though this technique is specific to Kubernetes, you can pretty much apply the same principles for any of the production grade orchestration framework, be it like a Docker Swarm or any of the cloud native environment. So let's assume a typical organization setup where you have the corp environment. And to add more complications, let's consider it to be the segmented environment, not the flat network. So now you have the corp environment, there is a firewall, and then the organization is using, let's say, the Kubernetes-based production environment to the right side, and there is a firewall in between. Now, as we just saw, in a Kubernetes, you have this pods that runs the bunch of the containers. Now, in order to manage the lifecycle of these containers, you should have some kind of a Docker registry. And security savvy organizations can actually have some internal Docker registry, or they could use different cloud services for that. So if an attacker is already in the corp environment, maybe by social engineering some of the employees, or by maybe exposing some of the services which is exposed to the internet unpatched, none of that is actually the unreasonable scenario. So once attacker actually gets foothold in corp environment, in order to pivot themselves from corp environment to the prod, they can use this Docker registry for that. So attacker has a different choices at this time. First, they can use some of the attacks that Emmanuel was demonstrating, like the file overlays in the operating systems, and then using some of the deleted Docker images that might have some sensitive details, might be some vulnerable Docker images, or they can upload the Docker image of their own choice. So any of this technique, let's say that attacker is able to upload the Docker image of their choice. And let's add a few things here, like they want to run themselves as a root. But again, remember that it's actually the root in a containerized system. And that Docker image might be vulnerable to any of the attack, like the RC or any of the attack that you can think of. And then attacker can wait and hope that their image is actually getting deployed using Kubernetes in the production environment. So this is how they finally got their foothold from a corp environment to the prod environment. So by foothold, I mean they just have a one container running in the production environment, maybe running as a root for that matter. Sure, you are your root, but you are in the container for that. So it's like a king in the jail. What you can do at that point, because now you have a foothold in the production environment, you can do some traditional things, like you can do the network scan. Now, one thing to remember here is the Kubernetes is an orchestration system. Traditional ways of performing a network assessment and then having a enforced network ACLs is still your responsibility. Kubernetes is not going to provide you it by default. In fact, bunch of the pods that are deployed in Kubernetes environments will be able to freely talk to each other. So the network scan is something an attacker is going to try definitely whenever they have some foothold in prod environment. They can try container breakouts. Remember, the containers are now pushed to the pod, which is a one more abstraction layer in Kubernetes. So the three techniques that Emmanuel discussed for the container breakouts, all of them are still applicable in this environment. So those can be tried out in this situation. Then they can actually try to compromise the API server. So the Kubernetes provides a control API server, which has the bunch of the plugins. It has its own marketplace in which people can push the different plugins. There might be vulnerabilities in that. It might be unpatched. It might be just left insecure for that. So compromising the API server is still an option. But in all these things that you can see, it's really not helping you much as a lateral movement or to maintain your foothold or to maintain your persistence within the production environment. Though these techniques are somewhat easier, it's not getting the complete fruit for an attacker for that. So at the last resort, what they can try to do is they can then try to evade the very basic security defense that has been added, that is to evade the role-based access controls. And it could be in the form of service tokens that they can use. So what are these service tokens? So this pods, as we were discussing, is the abstraction layer that Kubernetes provides, on which your containerized images are running. Now, in order for these pods to talk to the control API as well as to other pods, they need to have something called as a bearer token. In a Kubernetes environment, it's service tokens. And this service token is usually found at this location, which is in the screen. It's standard across all the pods for that. Now the pods, just like a Linux, they're associated with a namespace, and these service tokens are associated with a pod. In turn, they are also associated with namespace. Now, what we have seen in general and overall issue that could happen here is this custom namespaces can create a custom service tokens, and often a time your DevOps pipeline or overall people want to be more faster deployment, this custom service tokens might have more permissive role. Now, there are a lot of devastating role that you can assign to the service tokens, like creating a pod, updating a pod, or deleting a pod, meaning whoever gets hold of this service token, that pod or that adversary can now invoke the control API to perform those actions, all those authorization associated with those service tokens for that. So the create pod is like one of the sensitive permission in that case. Now these service tokens are also mountable, meaning if your pod has a specific service token, and if you are considering security from the beginning, and then now you want to share this service token across different pods in the same namespace, you can make them as a mountable service token, so that the other pods, when they are scheduled, can just mount this service token, and then they assume the same role that is already available for them. So by default, the service tokens are mountable. So imagine a situation where you are able to create a pod and then mount a service token, which is of a much more higher privilege than you would have originally got. That's like mounting the file system in case of a Dockerized environment. So to add to the agony here, so the root privilege container. So even if you are a root within the container, and we are calling it as the king in the jail, this specific path where the service tokens are present, by default you can read that if you are root. And if you are root, if you are not a root within the container, then Kubernetes will not let you read this path. But that's not a foolproof solution. There are a bunch of ways in which it's like a sudo. You can try to sudo within the Kubernetes world and try to read this service token path. So getting hold of this service token once you have a pod deployed in Kubernetes is not a difficult job. Any seasoned pen tester or red teamer would be able to eventually get to that. And if these service tokens are of a higher privilege, then that's a recipe for the complete compromise. So let's take like after this discussion and general understanding, let's consider one lateral movement example for that. So as we have seen, the attacker is able to deploy the Docker image with a root. So that container with a root is already present, and they deployed the pod. So now they are within the containerized environment, Kubernetes environment, with a container, and they have the root privilege for that. Now, with that, if that pod has a service token permission which lets them create the pod, then attacker can actually deploy the pod. Now, while deploying the pod, the Kubernetes gives you a nice way to mount whatever file system that you want for that matter. So here we are gonna use one of the attack that Emmanuel described, where, hey, I want to actually deploy the pod, and in the container which is on that pod, I want to actually mount the docker.sock or socket environment for that, which will then let me talk directly to the Docker daemon, which is running as a root, as we discussed. So this is as good as like a privileged container for me in the production environment. In order to make things more easier, Kubernetes also lets you create privileged container. Now, the privileged containers or the privileged pod, they basically share the same concept or the same theory, that you can now mount the host file system, and then you have a direct foothold to the kernel. Like at that point, you have a direct access to the kernel for that. So an attacker with this logic will be able to deploy the pod of their own choice and then start compromising the one node at a time to eventually perform the lateral movement and then have their persistence in a containerized environment for that. So all that, whatever we discussed, it's nothing new, or it's not like it's a new information that we are giving you. But where it lacks in general from the offensive security perspective is there are not lot of tools that let you do this. So imagine you're already in a containerized environment, and now you want to actually automate all of that so that then you can focus on real things like breaking out of container or maintain the persistence or perform the lateral movement. There are a bunch of choices that are there, and there are isolated tools present, but there is not a single framework that lets you plug all these tools and then create a coherent framework for the containerized environment. So that's the contribution that we think we're going to make here. So we are going to present our tool, the tool Shiva. So this tool, once you are within the containerized environment, is going to try the bunch of techniques for the lateral movement and the persistent. So it's going to check where you have access to the service token. Then does your service token already has the right authorization? If it is, then it is going to try to deploy the pod. And if it is able to be successful for that, it lets you SSH or exec into that pod. So this is a quick demo of that tool, and it's trying a bunch of the options, and eventually it deploys a pod of attacker's choice, which eventually let the attacker perform the lateral movement and persistence in the environment. All good. So we have seen different ways in which we can perform the container breakouts, different attacks, as well as the lateral movement, persistence. What about defense for that? So some of these defense techniques are specific to Kubernetes, they are similar to the different attacks that Emmanuel was describing. The first one is the least privilege for your service token, and it is similar to not having a privileged flag for your Docker environment. So especially in a Kubernetes environment, whenever you are creating service tokens and assigning them to a specific namespace, pay specific attention to make sure that the privileges associated with that are just the least privilege, that don't assign any overly permissive privileges there. Kubernetes also provides you a way to use the pod security policy. Now, in the pod security policy, I'll recommend that you disable all containers running as a root unless it is absolutely required, and then also disable the privileged pods, again, unless it is required. Because then though it will not completely stop the lateral movement and persistence, it will limit an attacker to the greater extent for that. In any production environment, your traditional knowledge of enforcing the network access control doesn't go away. You still have to do it. And even so, you have to do it even more efficiently in a production environment using Kubernetes. And then secure your container registry for with the different techniques like auditing, proper access control with zero trust monitoring to protect the attacks that Emmanuel was describing, and one of the example that we also saw for the initial entry point for an attacker. And that's about it. Thank you for attending our talk. Hope you find it useful.